Hello, welcome to my channel where you will get deep understanding of structural analysis and design concepts. In this series of videos, you will learn about influence line diagram right from basic concepts to numerical example. In this video, we are going to understand how to draw influence line diagram for shear force at a section of indeterminate beam using Muller Breslau principle. In my previous videos, I have already explained what is meant by influence line diagram and how we can apply Muller Breslau principle to draw the influence line diagram. Now in this video, we are going to understand how to draw influence line diagram for shear force at any section of indeterminate beam. So let us start. To understand how to draw the influence line diagram for shear force at any section for a continuous beam, we will solve one example and I will explain step-by-step procedure how to solve that example. So let us take this example. Draw influence line diagram for shear force at a section D at midpoint of span BC of continuous beam ABC. Span AB is equal to 4 meter and BC is equal to 4 meter, and we have to find ordinates at 1 meter interval. So this is the given beam ABC with span 4 meter each, and we are interested to know how will be the influence line diagram for this section, shear force at this section D. In previous videos, we have already studied how to apply Muller Breslau principle to draw influence line diagram for any function. So let us revise the steps. So if you want to apply the Muller Breslau principle to draw influence line diagram for any function, the first step is remove the ability of the beam to resist that function. Then second step is give unit displacement in the direction of that action, and then obtain the deflection curve due to unit displacement, and then the resultant deflection curve due to unit displacement itself is the influence line diagram for that function at corresponding point. So these steps we have already discussed in previous videos. Now let us apply this Muller-Breslau principle to draw the influence line diagram for shear force at section D. So first of all, we have to remove its ability to take the shear force at section D. So let us see how we can do this. So to draw influence line diagram for shear force at D, first of all, we have to remove the ability to resist shear force at D by cutting the beam at section D. So first of all, we have to cut the section at this location D to remove its ability to resist the shear force, and then insert a sliding device as shown in figure, and then apply a pair of unit loads at required section. So you know that shear force is always in pair. So we have to apply the pair of unit force in the direction of shear force to draw the influence line diagram. Now when we apply this force, what happens? This part, CD part, is lifted up like this, and this part will go down like this. At C there is support, but it is free to rotate at B, and therefore this beam will take the shape like this, and this shape itself represent the influence line diagram to some scale. Why I am saying some scale? Because this is not the influence line diagram of shear force. We will call this as the influence line diagram for shear force at D when this ordinate is equal to 1. When we make this ordinate is equal to 1, then we can call this diagram as an influence line diagram at shear force at D. So now let us see how we have considered which portion is to be positive and which is to be negative. Now please listen carefully that whenever the moving load or unit load is in between B to D, when the unit load is acting in between B to D, then reaction at C will be upward. When unit load is acting between B to D, unit load is downward. So reaction at C is upward. So in that case, suppose you want to calculate the shear force at this section, then it is nothing but, you know that shear force is summation of vertical forces. So on right side of this, there is only one force because our unit load is here. And therefore shear force is nothing but this reaction. Now this reaction is upward. And you know that from your strength of material concepts, the sign convention of shear force, if you remember, the shear force when we calculate from right side, then upward we consider as negative. So that means when the unit force is in between B to D, shear force is negative. And therefore, for this portion BD, we have shown the diagram on negative side. And therefore, for other portion, since it is opposite of that, we have shown the diagram above the line so that we get positive ordinate. So this is how we decide where to draw the positive ordinates and where to draw the negative ordinate. Now let us solve this problem. We are interested in calculating the ordinates at 1 meter interval. Now our problem reduced to this. We are interested in drawing deflection curve due to this unit force, and deflection curve will be something like this. This ordinate will not be 1 because we are applying unit force here. We don't know what is the force required to make this equal to 1. So we are applying unit force in the direction of shear force. First we will draw the deflected shape due to unit force, and then we will make this ordinate equal to 1. Then it will be called as influence line diagram. So now we are interested to draw deflected curve for this case. That means we are going to solve this beam by conjugate beam method to calculate the deflection. So let us see how to draw the conjugate beam for this case. Now since we want to get this shape of influence line diagram due to this unit force, these are the force applied in the direction of the shear force. So to get this diagram deflected shape, we have to draw the conjugate beam for this case. So let us draw the conjugate beam for this case. You know that conjugate beam is an imaginary beam which is loaded with M by EI diagram of this original beam. Therefore, we are interested in drawing the bending moment diagram for this beam. So let us see how to draw the bending moment diagram for this case, because bending moment of this beam will be loading on the conjugate beam. So for that, first of all, we will draw a free body diagram of part DC. So when we apply the summation of vertical forces equal to 0 to this part DC, we get reaction at C is equal to 1. Because this is upward 1, we will get reaction at C is equal to 1 in downward direction. So now because of this, we will calculate what are the bending moments at various positions. Now you know that this is a simple support. This is a simple support. So bending moment at A is equal to 0. Similarly, bending moment at C is also equal to 0. Now to calculate bending moment at B, so we will take moment of forces from the right side of B to calculate bending moment at B. Because we know this reaction, this RC is equal to 1. So bending moment at B is equal to force into perpendicular distance. So force is 1 and distance is 4. So due to this RC, bending moment is 1 into 4. And due to these forces, these are equal and opposite 1. So moment due to this will cancel each other. So there will not be any moment due to these forces. There is moment only because of RC. And this moment is equal to 1 into 4. So at B, the bending moment is 4. So now bending moment diagram will become a triangle with 0 ordinate at A, 0 ordinate at C, and at B there is ordinate 4. And you know that conjugate beam is an imaginary beam which is loaded with M by EI diagram. So we have to divide this 4 by EI. So we consider 1 upon EI is equal to K. So ordinate at B will be 4K. So let us see how this diagram will look like. Since the reaction at C is downward, so bending moment at any section will be minus this 1 into x. So it is a hogging bending moment. And you know that if the bending moment is hogging, then load on conjugate beam is downward. So let us see how will be the conjugate beam. So we are drawing conjugate beam for this beam. So we know that bending moment at A is equal to 0, which is shown here. Bending moment at C is equal to 0, and bending moment at B is equal to 4K, which is hogging bending moment. You know that load on conjugate beam is equal to M by EI diagram. So this ordinate is 4K, and since the bending moment is hogging, load on conjugate beam is downward. So conjugate beam is an imaginary beam which is loaded with M by EI diagram. So this is the first step to draw the conjugate beam, that is to draw the load. And second step is to modify the reactions. So here it is a simple reaction. So here also it will be simple support. So simple supports remain as simple support in conjugate beam. This is also a simple support. It will remain as simple support in conjugate beam. This is intermediate support. Intermediate support becomes intermediate hinge in conjugate beam. Now at these locations, since we have introduced some deformation, and deformation or deflection in original beam is moment in the conjugate beam, and therefore since we have introduced unknown displacement at point D, we have to replace that displacement by a moment in conjugate beam. So this is how we draw the conjugate beam for this case. This is just to revise how we modify the supports in conjugate beam. So in original beam, if the support is simple support, that is roller support or hinge support, it remains as roller and hinge in conjugate beam. Fixed becomes free, free end becomes fixed end, interior support becomes interior hinge, and interior hinge becomes interior support. So this is how we modify the supports in conjugate beam. Since in this case we have introduced unknown displacement at the location of D, we have to draw an unknown moment in conjugate beam, which is shown like this. So this is that moment which is shown for unknown displacement in conjugate beam. So interior support becomes interior hinge and simple supports remains as it is. And load on conjugate beam is bending moment of original beam. Now if you calculate bending moment in this conjugate beam, you will get deflection in original beam, and therefore we will write general equation of bending moment for portion AB. Then we will write general equation of bending moment for portion CD, and we will also write general equation of bending moment for portion DB. So let us see how to write the bending moment equation for these different portions. So to write the general equation of bending moment, first of all we have to calculate the reactions. So to calculate reaction, first we will consider this portion and we will apply the equilibrium condition. Bending moment at B equal to 0. You know that this is a internal hinge and therefore bending moment at B is 0. When we say bending moment at B is 0, that means we take the moment of all the forces from one side only. So apply this condition to the left part of this triangle. So there are two type of forces. One is this reaction and second is this triangular force. So moment due to reaction is Ra into 4, force into perpendicular distance. And moment due to this triangle is area into distance of CG. So area of triangle is half base into height multiplied by distance. Now what is the distance? Distance is always measured from the point where we want the bending moment. So we want bending moment from B. So distance is 1/3 of 4. So it is 4 by 3. So if you apply this condition, you will get reaction at A is equal to 2.667 K, which is in upward direction. Once you calculate vertical reaction at A by considering bending moment at B equal to 0 for this left part, next is to calculate reaction at C. How we can calculate reaction at C? We can consider this complete beam and then we can apply summation of vertical forces equal to 0. Then we can get the value of reaction at C. So if you consider complete beam ABC and apply summation of vertical forces equal to 0, you get Ra plus Rc is equal to, this reaction is equal to total load. What is total load? Is area of that triangle, that is half base into height. So if you solve this equation, you will get reaction at C is equal to 13.333 K upward. Now next is to calculate this unknown moment M. Now let us see how to calculate that unknown moment M. Now we have calculated vertical reaction at A 2.667 and vertical reaction at C 13.333 K in upward direction. To calculate this unknown moment, we can consider this right part and we can apply bending moment at B equal to 0 considering right portion of this triangle. So let us calculate this moment by considering bending moment at B equal to 0 and calculating taking the moment from right side. So if you consider portion BC and apply bending moment at B equal to 0, moment due to this vertical reaction, since this is upward force, it is positive 13.33 multiplied by 4. 4 is the distance. So force into perpendicular distance minus moment due to this triangular force, which is area of triangle half base into height divided by distance from the section. We are taking bending moment at B. So distance is 1/3 of 4. Then moment of this M. So we are considering the direction like this. This moment is similar to the moment of vertically upward force. So therefore we are writing here plus M. And if you calculate, if you solve this equation, we get M is equal to 42.667 K. So this is how we can solve this conjugate beam and calculate the reaction and unknown moment in the conjugate beam. Now for this beam, we have drawn this conjugate beam. Now in conjugate beam, we have to make this ordinate is equal to 1. When we can make this ordinate is equal to 1, then this deflected shape is called as influence line diagram. So we know that this deformation or deflection in deflection in this deflected curve corresponds to this M. So moment in conjugate beam is deflection in original beam. So this deflection corresponds to this M, and therefore we have to divide all the ordinate of deflection due to this one by 42.667 K, because this we want to make 1 and this corresponds to this M in conjugate beam, and therefore we will divide all the ordinate by M in case of influence line diagram for shear force. Now we will write the general equation of bending moment for various portions, and then we will calculate the bending moment and deflected curve. Now to write the general equation of bending moment for portion AB, we will take a general section here at distance x from A. So we can write here the relation. Suppose this distance is y, so y upon x is equal to 4k upon 4, and therefore we get y is equal to x. Now what is bending moment? Bending moment is force into perpendicular distance. So we are writing the equation here. So bending moment is equal to this RA into distance. RA is 2.667 K into x minus this small triangle multiplied by its distance of CG from the section. So area of triangle is half base into height multiplied by its distance, that is 1/3 of the x. So if you simplify this, you will get this equation as a general equation for portion AB, general equation of bending moment for portion AB. Similarly, we can write general equation of bending moment for portion CD and for portion DB. To write the general equation of bending moment for portion CD, we are writing the equation from C to just right of D, because at D there is a moment. So we are considering section from C to right of D, and we are considering C as origin. That means we are measuring the distance x from C. So if you calculate the relation y upon x is equal to 4k upon 4, so we get same relation y is equal to x, and therefore bending moment is equal to this reaction into distance, that is 13.33 in k into x minus kx cubed by 6. If you derive this, you will get this equation. Now we will write equation between D to B. Just I want to make one correction in previous slide, that when we calculate M, that is this moment, we get negative value. So please note that this is a negative value. That means whatever direction we have assumed here anti-clockwise is not correct, but the direction of M is clockwise. So remember that the direction of M in this case is clockwise. Now we will write down the equation for portion just to the left of D to B. So if you take the section here, this moment will come into picture. So we are considering C as origin, means we are measuring the distance x from C. Therefore this equation remains same, which is for CD, and in that equation you have to add just this moment M. So we know that this moment is clockwise, so here it is just has same direction, that of downward force, and therefore we are taking it minus. So this equation becomes 13.33 kx minus kx cubed by 6 minus 42.667. Now we have derived all the three equations, that is general equation for AB, general equation for CD, and general equation for DB. Now we will write all these in tabular form, and then we'll find out the deflected shape, and finally we will divide this bending moment ordinate by 42.667 to get ILD ordinates. So let us see how to write the tabular form. So just now I told you that after deriving the equation, we have to substitute the value of x in the equation of bending moment and calculate bending moment for conjugate beam at 1 meter interval. And to find ILD ordinate, we have to divide all the ordinates by m, that is 42.667 K, to get ILD ordinate. Now this is the beam for which we are drawing the influence line diagram for shear force at section D. So we will take the section at 1 meter interval. So from A to B, there are 1, 2, 3 and 4 sections as shown here. So distances from A are 0, 1, 2, 3, 4. And for this we will be using the general equation of AB with origin at A. So substitute value of x is equal to 0, you will get this ordinate, 1, you will get this ordinate. Similarly, you can calculate for other ordinates. Then for portion BD, we have to take two sections. One is here, section number 5, and one is just to the left of D. So section 5 and just to the left of D, which is 6. So we write here 6 left. So what is the distance of it from C? We are measuring distance from C. So its distance is 3 meter and 2 meter. So we have written 3 meter and 2 meter. So substitute the value of x in respective equation and get the bending moment ordinate. Similarly, 6 right means this ordinate. 6 right. So remember that at section D, we have two ordinates. One is 6 left, which is this, and 6 right, which is this. So we write here 6 right, then 7 and C. So distances we are measuring from C. So here distance is 2 meter, 1 meter and 0 meter. So we have to substitute these values of x in the equation. We will get these values. Now these are the deflection due to unit shear force which we have applied at D. But we don't want due to unit force, we want this ordinate to be 1. And therefore, we have to divide all these ordinate by 42.667, which is the value of M in conjugate beam. So if you divide all these ordinate by 42.667, you will get these ordinates. Now how will you check this? So you must get addition of this and this equal to 1. So this is 0.594 and this is 0.406. If you add this, you must get 1. So this is the influence line diagram for shear force at any section D. So this was the given problem to draw the influence line diagram for shear force at section D, and this is the solution. So remember that this ordinate must be 1. So if you add these two, you must get 1. So I hope you must have understood how to draw the influence line diagram for shear force at any section D. I hope you will find this video useful. In next video, we will see how to draw the influence line diagram for bending moment at any section and for support moment. So stay connected, subscribe to the channel to get the notification of new videos which I upload on this channel. So thank you for watching this video. Thank you very much.